Yeah, I click on the go live. Yeah, fine. It's showing on the YouTube, no problem. Yeah. Yeah. Yeah.
Yeah, sir, you can start. Thanks, sir, thanks.
Sir, only thing is that YouTube is not showing. Only that problem with the YouTube, but you are the live on the for the learning.
So people can see me now.
Yes, yes,
Yeah.
yes. So
They can hear also.
yeah, yeah, yes. You can edit that.
But this screen won't come.
No, no, no.
Huh?
Which screen?
The
Yeah, that
slide.
will also come. That will also come. Yes. So don't worry, everything is fine.
Like this? No, I can't see that. It's okay, na?
So, all the questions.
Yeah, then it's starting. Hello. Welcome to NPTEL NOC course on Point-Set Topology Part 1. This is a live session number 2. As usual, the live sessions are meant for interaction. So you have to ask questions and then I answer. That is the mode. However, today I have one special task for you. That also I will do. I will take care of that also. But please start asking your questions. Last time I have given you very clear instruction that by now you must be ready with this, your questions and just load them. Then we will know that. Okay. One person here, Sarthak Vijay. Today he is going to contribute in a very positive way. So that I will tell you, maybe we can listen to that first and then I will answer other questions. So his remark is on, let me show you the slide if it's possible. Where is this slide here now? Hello, how do I show this slide? Hello? Slide. I need to show a slide. I won't read my own slide.
So this is another.
Huh? Where is the slide? Where did you do that one? Yeah. So this is unions here. Quotient space. Yeah. Extending neighborhoods is module 27. There is this nice lemma here. It says that if you have a subspace Y of a closed subset of a topological space, and A is a subset, A is any subset of X, V is an open set in X such that A is contained inside V. Then U is an open set in Y such that A intersection Y contained inside U contained inside V intersection Y. Okay, then you can extend this U to an open subset V prime in X such that if A is contained in V prime contained inside V, extension means what? V prime intersection Y is the given U. So this lemma there is no problem. This is also useful also. and we have seen the proof of this. I'll just show you how it was done. Okay. Now, as a illustration of the usefulness of this one, I included a proposition. So this proposition, you know, the proof of this proposition, namely it is now about, so let me just repeat the proposition. So now X is, first of all, increasing union of subspaces Xi, each of them closed in the next one, right? X1 contains X2 and so on. And we have coherent topology. Now B is an arbitrary subset of X contained inside some W, contained inside X, okay? Such that for each I, if you intersect W with Xi, that will be a neighborhood of B intersection Xi inside Xi. Then the claim is W is a neighborhood of B in X. If you replace this neighborhood by open neighborhood, then this is obvious from the definition of the coherent topology. Okay, so one wished that such a result is true, and this is used in many classical books also. Okay, now what we have given here is the proof. In the proof, I am saying that you have to apply lemma, previous lemma, where previous lemma can be applied with V equal to Xi intersection W for each I, provided you know that this is open subset. Okay, because in the lemma we assume that V is open. But given that W is such that W intersection Xi, that is V, now you should take V, that is only a neighborhood of this B intersection Xi inside Xi. So you cannot apply it directly. So my first thought was maybe I should just take V interiors in each time and apply that one. The problem is, if you take V interior, you don't have the hypothesis that Xi, this one, you see B, this each I, W intersection Xi is a neighborhood of B intersection Xi in Xi, right? If you take the next one, namely you take W intersection Xi plus 1, take its interior as V, that may not even contain B intersection Xi. That is the problem. Okay, so therefore the proof is incomplete here. Of course it is incomplete even otherwise. So what I am telling is, even trying to repair this one by putting V instead of V, putting interior of V for the next one, it is not possible. Okay. However, the point is, now what I want to say is, it is never possible. In other words, this theorem itself is wrong. Now that is a bit of a shock, because this is there in classical books. Namely, one of the books that I have meticulously referred to for this part of the course is Lundell and Wingram's book on CW complexes. It is very clearly stated, not only this theorem is there, a big generalization of this theorem is there, and this theorem is quoted as a easy corollary to that. Now, if you go back to the proof of this more general statement they have, it's a very, very complicated proof. So I thought I have a simpler proof directly for this thing. Okay, but that is not possible. Now you go back to the proof in the original, in that book, there also Exactly the kind of mistake I am making here is made there. You understand? So same proof, it is not same proof, but the same kind of mistake occurs there also. So I am now very sure that this theorem is not true. Well, to say that something is not true, what you have to do? You have to give a counter example. Otherwise, there may be another proof. Some other proof may be there, right? Yes or no? So, here is a counter example. I will show you the counter example also, which is quite educative anyway. Okay, so let us go to the another slide here. Yeah. So here is the counter example. Are you with me so far? Do you have any question before we go to the counter example? Anybody else has any questions? Do you understand what is going on? I will tell you where even the mistake occurs. That I will explain you while explaining the counterexample. Okay? So here is a counterexample. Start with this R omega, which denote set of all sequences of real numbers which are eventually zero. Okay, you can think of this as direct sum of, yes, the recorded session will be there on YouTube, yeah, sure. So, come back, the R omega here I am talking about, you can think of this as direct sum of infinitely countably many copies of R. You can also think of this as a set of all sequences, real valued sequences, which are eventually zero. Say, let us say xn equal to all those sequences, s1, s2, s3, sn, then sn plus 1 onwards, they are all zero. Okay. In particular, this xn is nothing but r power n, right? S1, S2, Sn, any number, any r can be there, any real values can be there. After that, 0, 0, 0, 0. So r cross 0 contained inside r square cross 0 contained inside r cube, and so on. There is a clear, sequence of spaces x1 contained inside x2 contained inside xn, and so on. Then R omega is nothing but the union of all these things. So this is the clear, exact way how the theorem would have been applied here. This is very special case of that, right? So R omega is nothing but, this is x. X is nothing but what? Union of all the xi's. Okay, at some stage, the sequence must be given any sequence, given any element here. So after some stage, it must be 0, so it will be inside that xn. So union of xn's, all xn's is equal to this R omega, which I am calling it as x. Okay. Each xi is given the topology homeomorphic to R power I. Xn is homeomorphic to R power n. Right? So give that topology. Then Rn minus 1 contained inside Rn will be what? Will be a closed subspace. So Rn, Xn contain Xn plus 1 and so on, they are all closed subspaces of one another. Okay, so that is also satisfied. Right? So what you have now is, after this one, on Xn, on X, namely R omega, give the coherent topology. Okay. Recall what's a coherent topology? Coherent topology is nothing but something is open if and only if intersection with each xn is open in xn, or You can put it in the closed set also. Something is closed if and only if intersection with each xn is closed in xn, right? So that is the coherent topology. So I have R omega coherent topology. So in this situation, I want to show that the claim of theorem is wrong, okay, is false. For that, what I should do? I will produce a subset here such that another larger subset such that the larger subset intersected with each xn is a neighborhood of the smaller subset intersection with each xn correspondingly. Okay, but what? But the larger set is not a neighborhood of this set in the whole space. Okay, so somebody is saying any finite dimensional subspace of a nonlinear space is closed. That is correct, but I am not using that here. Okay, you see, I am not taking the R omega as a nonlinear space. I am taking, what I am taking? I am taking the coherent topology. So I don't want to get into that muddle here. Okay, the coherent topology is usually stronger than the norm topology which you get R omega as a subspace of L infinity space. L1, L2, L3, you can think of this R omega sitting inside all these LIs. We have discussed them quite often. So, but don't get carried away here. On each subspace, it is the nonlinear space, it is Rn. So you can choose any norm there. All the norms are equivalent. That you know, right? So I can take L2 norm, no problem. Or I can take L infinity norm. Alright. But when I am going to R omega, which is infinite space here, infinite dimensional vector space, right? On that one I am taking the coherent topology. Okay? So be sure of that. So now here is my example, the set W and set B. Okay, let us have this notation Sn, set of all points in Xn. That means what? S1, S2, Sn, and then 0, 0, 0. Only such things, such that its infinite norm, this is supremum norm, L infinity norm. L infinity norm is less than 1 by n. What does this mean? Just means all the SIs, modulus of SIs are less than 1 by n, that's all. Maximum of all the modulus of SIs is less than or equal to 1 by n, that's all. So this is the short notation we just recall. This norm infinity denotes the maximum norm here because they are finite here. So but it keeps changing, so I will use this supremum norm here, which is same thing as maximum norm because I am taking only elements of Xn. Okay, so this is my definition. And take S as union of all these Sns. So that is going to be my W. Okay, union of all these Sns. Now I have given you a picture here. This line here is a subset of R. R cross 0 cross 0 cross 0. Here I am taking -1 to +1 because n equal to 1. Right? Mod S1 must be less than 1 by n. And all other things are 0. So this thick line is my S1. What is S2? S2 will be from this square -half to +half product with -half to +half. This is the square there. Okay, that is S2. S3 will be what? -1/3 to +1/3, take product 3 copies. So this is the box here, and so on. So I can't draw pictures more than that one, right? So in 3 dimension I have shown you what is I am taking here. Look at this one. All of them contain the 0 element of R infinity, R omega, 0, 0, 0. Okay? Not only that, if you intersect this set S with R1, which X1 is R, what is it? It is just -1 to +1, the closed interval, or open interval, sorry. open interval. So that's the neighborhood of 0. If you intersect with S2, intersect with X2, namely R2, what is it? It is this open box, open rectangle here, minus half to plus half. That is also neighborhood of 0. If you take S3, that will be open neighborhood again, this box, and so on. So 0, for 0, S intersection Xn is a neighborhood of 0 for all n. Right? So according to theorem, what should be the conclusion? The conclusion should be that 0 must be a neighborhood of this, S must be a neighborhood of 0 in the space X itself, in the space R omega. Right? So I will show you that that is not the case. The important thing here you must observe is the following thing. There are few portions here of -1 plus 1, some portion of that is not contained in the larger open set here in R, in the R2. That some portion of R2, whatever the open subset, that is not contained in the next one. You see, as n increases, the size of this box becomes smaller. So it will leave out some small portion of this one, no matter where you take. Okay, so it is neighborhood of only smaller one. But as n keeps increasing, there will not be any neighborhood, because as n increases, 1 by n tends to 0. So that is the whole idea. Right? So idea is fine. So we have to implement it, we have to argue it that this is correct idea. So how do we prove that this S is not a neighborhood of 0? Can you see that? That is the only thing that remains to be proved. Okay. So in R omega there is no neighborhood, is what I have to show. In R omega. What is neighborhood in R omega? Neighborhoods in R omega, I mean open subsets. We want open subsets, right? Open subsets in R omega mean intersection with each Xn must be open in Xn. Right? So that there is no such thing is what I have to show. Okay. So suppose U is an open subset of X such that 0 belongs to U contained inside S. So that is the claim, right? Suppose that is true. Then U intersection Xn is an open subset of Xn, because U itself is an open subset of the whole of X, right? And these Xn's are subspaces. So U intersection Xn will be an open subset of Xn. Also U intersection X will be contained S intersection Xn. Right? Because U is contained in S. Right? Now, what is the maximal open subset of Xn which is contained in S intersection Xn? So that is just Sn. Maximal open subset of this S intersection Xn, which is contained, inside S intersection Sn. Okay, so that's what I mean. Maximum open subset of Xn is contained inside S intersection Xn. I have claimed that this is an open set. Okay, now, if it is an open subset, it will be contained in the maximal one. So look at this picture. What is the maximal open subset contained inside S intersection X1? S intersection X1 is precisely S1. So that is -1 to +1. What is it contained in S2, in X2? This portion will not be there now. Okay, anything bigger than -half or less than -half, comma 0, those things, those points have no neighborhoods inside this x2 intersection s1, because this s has become smaller here, just this portion. This is the this open rectangle is a maximal open subset contained inside this S intersection xn. Okay, each time that's what's happening. Therefore, this is the claim. This claim is first of all that the maximal open subset of Xn, which is contained in S intersection Sn, is Sn. Therefore, this being some open subset, this must be contained inside Sn for all n. This is now very easy to implement. U intersection Xn is contained inside Sn for all n. Okay, just look at one single point, S1, 0, 0, 0, okay, contained inside U. This point will be inside U intersection Xn for all n, right? Because all other points are 0. It will be inside S1, it will be inside S2, inside X2 and so on. So this implies that this point S is inside U intersection Xn for all n. Therefore, this S must be inside Sn for all n. But what is the meaning of S is inside Sn for all n? Mod S1 must be less than 1 by n for all n. That is the only condition, because all other coordinates are 0 anyway. The supremum norm here for all of them must be less than 1 by n. This norm infinity I have defined here, norm infinity is less than 1 by n. So mod S1 must be also less than n. If mod S1 is less than 1 by n for all n, what happens? This S1 must be 0. So that is the only point. Okay. So singleton 0 is not an open subset in R, and that is clear. Okay. A U intersection x1, if it is singleton, it won't be open inside R itself. So forget about being open inside R infinity. That's the counterexample. So it was a surprise for me also. However, I am quoting that this is a useful theorem and so on. It is useful for certain things, but the theory of CW complexes wherein it is useful, there writing down certain proofs becomes somewhat easier if you use this theorem. But those theorems are true even without this theorem. So there is nothing very serious happening. Okay. So certain in many of these books, whatever proofs have been written, they have to be rewritten, that's all. All I would be sure that it is usually used in proving certain theorems for product of CW complexes. Since those things are beyond the core, beyond this course, I cannot give more explanations of that right now. So that more or less completes this one. With a big thanks to Sarthak. Okay. So you people are welcome to make those comments. That's another lesson for you here. Okay. So now, if you have other questions, you can ask. There's quite a few time left out, so I can try to answer them. So far the course has come up to, this is ninth week, 10th week. So 9 weeks you have finished. I think now you are studying what? You must be studying Hausdorffness, regularity and so on. So if you have any questions till then, you can ask in other areas. That's a good question. Is it metrizable? You can try. There is an easy way of metrizing it. Namely, you can take difference of any two elements. It will be in some Rn, right? So you can take the distance between those 2 points. That's all. The question is, you have to see whether this will become the same topology. Now usually the metric topology will be weaker. Okay, so that is an interesting question. You can answer to yourself. No, there is time. We have started much later, okay? So people need time. So whatever I wanted to say, that is done. So they are coming up with some questions, so I have to wait. There is some strange question here. Is there a non-compact Hausdorff space with compact tense subset in? So compact is a non-compact Hausdorff space. Hausdorff space, any compact subset is what? It's closed. Right? Any compact subset is in a Hausdorff space is closed. Have you studied that? That's one of the theorems we have proved. So if it's dense, what happens? It's the whole space. Right? If you remove T2 dash, then there are easy ways of constructing this also. You know, you have got one big tool with you, Sierpinskification. take any space, add extra point such that what? Such that the only open set containing that extra point is the whole space. Right? Sierpinski specification of any space. What happens? Sierpinski space is always compact. Problem with Sierpinski space is it is highly non-Hausdorff. Even if you start with a Hausdorff space, when you add this extra point, it will not be Hausdorff. Right? So you have the answer there also. You know, compactness and Hausdorffness together, that makes life very, very easy, very, very stringent. There is not much room there. Okay. That's why, Hausdorffness is given so much of importance. To the extent that, why they are called Hausdorff space? Have I made that remark earlier? Because Hausdorff started the axioms of topology along with the condition Hausdorffness, what is called as Hausdorffness nowadays. Namely, any two distinct points can be separated by open sets, disjoint open sets. That's why they are called Hausdorffness. So Hausdorff, who is the inventor of, most of is the point-set topology, he gave so much of importance to this axiom. He put this as a part of the axioms for topology itself. It's so important. So let me answer first question which Sarthak Vijay has taken. You know, the whole idea of pre-recorded discourses You can do it in your own fashion, in your own time. Okay, the only thing is, when you have taken exams, there is a time bound. But that is a reasonably good time bound. You don't have to, if today you didn't come, okay, weekend, you can finish off. That much you have to do. Okay, so you have to catch up. The point is, even submission of weekly things, there are enough time also. It's not as if today you get the questions and tomorrow you have to submit. Okay, for submission of weekly assignment and also a final exam, those things are fixed. But there is, I think, there is enough time. If you need more time than that one, that is also possible. You can always study this one on your own, but you won't get marks. That's all. Okay, you won't get a certificate. For certificate, you have to do it within time bound. But that time bound is also not as if today. Whereas unrecorded lessons, regular sessions. Suppose this was you are attending a regular class. I have given my lecture and it's over. Only thing is, sometimes even notes are not there. Only thing you have to refer to some, your friend's notes and so on. So that is not the case. So there is a lot of advantage here. You have the full notes, you have the recorded things, you can listen to it in your own fashion. So don't get no question of anxiety here. Do it in your own time. The only thing is, if you need more time for this one, you will have to cut down other activities. You can't do everything at the same time. That's all. Okay. So coming to this center of radius and so on, same center, same radius. What is this question? His question says, you have metric space. Okay. Forget about it's coming from a vector space and a norm and so on. That is not needed. Okay. Closure of an open ball is the closure ball in a metric space. That's what you have to show. And that is correct. Okay. First of all, what is the closure? It's very two different definitions. A closed ball means what? Distance less than equal to some r. Right? So all those points are precisely the closure is what you have to show. So you try that one. Take any point which is bigger than that one. That means, so take any point which is not in the closed ball. Show that that is not in the closure. Then one thing you would have shown. Alright? How do you show that? You must produce an open ball around that point which you have taken outside, which does not intersect this closed ball at all. Right? That's easy. There's no problem. Right? Right? So one way is clear. Now, to prove that every point in the closed ball is a closure point. Interior is no problem at least, because there are already points of that. Take any point on the closure. What is the meaning of closure? Closed ball. Equality, right? Take a point there. Now take any neighborhood of that point. Every neighborhood of any point in a metric space contains an open ball centered at that point, right? Again, use triangle inequalities to say that will intersect the point, intersect the interior. Okay. All right. You see, the pictures may be misleading, but they give you some idea how to work out. For example, so just to check whether your answers are correct, You take different metrics like discrete metric. Okay. If you take discrete metric, what is a closed ball and what is an open ball? When the radius is say less than 1, the closed ball and open ball are just singletons, right? So it's a closure. The closure, if you take in the discrete metric, the closure ball of radius 1 is the whole space. Right? So you see, that's why I asked you. So if you you have to be very careful when this is true and when this is not true. Okay. Yeah. My question is when this is true. Non-linear spaces are fine. Yeah. When this is true means what then? The closed ball of radius of anything is a closed set, but is it the closure of the open ball? That is your question. It should be like that, right? Closed ball of any radius, whatever it is a closed subset. That is shown the first time. Okay. In the discrete metric, if you take the CLX1, that is singleton set, right? That's what closure of singleton set is singleton itself. But it is a closed ball also with radius different. With a radius different, you have to take less than 1. Take radius less than 1, then it's a closed ball. Okay, the radius will be different, that's all. So instead of directly giving you, yes or no answers, I am trying to tell you how to work it out. Think of this way, okay, I am right here, but always guided by some proper examples. Don't use all the time pictures, that's all. So anyway, this is a good question. So I am a bit confused with your notation. I have not used this notation B square bracket 01 for closed ball. I think you wanted a closed ball. I have not used that notation, okay? So the equality is true in many cases, not just in the case of vector spaces. So when is means what? You can give sufficient conditions, if and only if condition, all that you have to think about it, so you can think about it. In any case, Sarthak, you people can contact me. You have my address, right? Even if the discussion forum is closed and so on, I don't know. I think it will be open till the exams are over. That is what I think. But if there is a problem that the TAs may not answer and so on, you can directly copy your questions directly to my, just the way you did for the other question. Send it to me through Gmail. Okay, you have my address. So send it to me Gmail. I will take care of your questions. First of all, you should formulate in the general setup, use just different notation. So 0 and 1 will make you think about only real line or something. Okay, you want any point x, okay, any r is the r x, that is my notation, and brx closure, okay, is the closure equal to the closure box. That is your question. Or make this assumption, and then what can you say about the space itself, about the metric itself, not the space in fact. So when such a thing is true means that, you see, the question should be formulated like this. For every point in X, suppose the distance has the following property, namely the ball of radius r, whatever r is, r any positive number, okay, its closure is equal to the closed ball. Okay, so it is not B01. What do you mean 01? It is, x is the center, so Bx, comma 1. Okay, so why 1? You can take any r, Bx, comma 1 instead of Bx, comma r. That is the correct thing. Or y such that distance between x and y is less than r. Okay. Now equality, put equality, is this the exact closure of Bxr is the question. So that is the way you should formulate it. Try your question, try your answer. Okay, this way, even if you are not able to answer it fully, you will understand what is going on. Look at various examples. Okay, what happens to the closure and so on. Okay. Once again, assuming X is a vector space is useless, almost, unless the vector space structure and the metric have something to do with each other. If you say it is a non-linear space and the metric coming from there, then this will be automatically true. That's what I told you. That's easy to prove. Okay, for a non-linear space, suppose D is the metric induced by the norm. That's a different game altogether. Okay, just assuming underlying space is a vector space is no good at all, because any uncountable set will be a vector space. Any uncountable set is homeomorphic to bijective to R, bijective to R square, bijective to R infinity, and so on. So that is not a very good thing. Okay? All right? I have given you many other metrics. Start the metric, you can change the metric to bounded metric and so on. Have you done that one all or not? The new metric D equal to D, capital D equal to minimum of dxy or 1. There are such things also, no? They will be the same topology. So closures, etc. will be the same, but metric distance metric will be different. You see? So there is a lot of scope here to understand what is going on. Right? Okay. So once again I tell you, if you want extra live sessions, the NPTEL is ready to do that. Yeah, D divided 1 plus D is also another metric, is bounded metric. So if you want additional sessions, you have to positively request it in the forum. Send the feedbacks. The NPTEL team will look into that one. Send an email to me also if you want. So then we will try to arrange one more. In any case, there will be just one more live session. If you want more of them, okay, you have to come up with questions. I am not going to dole out just like that. I am ready to have this interaction, but you have to keep asking questions. Okay, now if you don't have any more questions, we can stop here. They still asking questions. I have told them if now there is no more questions, then we will stop. Okay, thank you. Thank you. See you again some other time.